You ever notice how your laptop gets kind of warm on your lap? Or, why the back of your fridge is always hot? Well, that's not a bug, it's a feature. A fundamental rule of the entire universe, actually. So today, let's dive into the big mystery of why, when it comes to energy, you can never ever get out exactly what you put in.
I mean, for centuries, we've been absolute masters at turning heat into power. Think about it. From those giant steam engines that kicked off the Industrial Revolution all the way to the super complex engines in our cars. We burn fuel, we create heat, and that heat, well, it pushes pistons and it turns turbines. It literally powers our entire world. It's an incredible thing we figured out.
But there's always a catch, isn't there? We pour a massive amount of energy into these machines, but we don't get anywhere near that same amount of work out of them. So the really big question becomes, where's all that missing energy going?
The answer is, well, it's pretty staggering. In a typical power plant, the kind that generates your electricity, more than 60% of the energy from the fuel it's burning is just lost, gone. It doesn't become electricity, it doesn't power your lights, it's just dumped into the environment as waste heat. Over half?
Okay, so you might be thinking, well, that's just bad engineering, right? Like, if we just got a little smarter, we could build that perfect, 100% efficient engine. But the truth is, it's way deeper than that. This isn't a design flaw we can fix. It's a fundamental law of physics. And to get why, we have to start with the first, absolutely unbreakable rule of energy. This is the bedrock for everything else we're going to talk about, the law of conservation.
The first part is super simple. You can't just create energy out of thin air. It can't be magicked into existence. You always have to get it from somewhere.
And it works the other way, too. You can't just make energy vanish into nothing. Poof, gone. Nope, it always has to go somewhere. All you can ever do is change it from one form, like the chemical energy in gasoline, into other forms, like motion and, of course, heat. This whole idea is wrapped up in what we call the first law of thermodynamics. You can think of it like a super strict cosmic accounting system. It says that the change in a system's internal energy has to perfectly match the heat you add to it minus whatever work that system does. Every single bit of energy has to be accounted for. No exceptions. A really great way to get this is to picture a system's energy like a bank account. Heat you put in, that's a deposit. The work the system does, like moving a piston, that's a withdrawal. The first law just says that your final balance has to reflect all those deposits and withdrawals. Nothing can just disappear from the ledger. So, if energy is always conserved, we're right back to our big question. Why can't we use all of it? And to get that, we need the second rule of energy. And folks, this is the one that explains the universe's built-in inefficiency.
And it all boils down to this one crucial, kinda weird concept: entropy. Entropy is basically a scientific measure of disorder, of randomness, of chaos. And here is the absolute key. The more disordered and chaotic a system gets, the more of its energy gets locked up in a way that makes it totally useless for doing any work.
This visual here just nails the concept. On the one side, you've got this beautiful, perfectly ordered ice crystal. Every single water molecule is locked in its proper place. That's a state of low entropy. But on the other side, that ice has melted into a puddle. Now all those molecules are just a chaotic mess, bouncing around randomly. That is a state of high entropy. Which brings us to the famous second law of thermodynamics. It says that for the universe as a whole, disorder, entropy, is always on the rise. Things naturally go from order to chaos, and they never spontaneously go the other way around. This law is actually what gives time its direction. It's why an egg can fall and break, but you'll never see the broken pieces fly back together to unbreak it.
A perfect way to think about this is the game 52 Pickup. Tossing a perfectly ordered deck of cards into the air and making a giant mess, that takes basically zero effort, right? That's a spontaneous jump to high entropy. But getting down on your hands and knees, picking up every single one of those cards and putting them back in perfect order, that takes a lot of work. You're literally fighting against the universe's natural tendency towards disorder.
So here it is. This is the big answer. To make an engine actually run, you can't just turn 100% of your heat into useful work. Why? Because that would be like creating perfect order, a piston moving in one direction from the chaotic, disordered motion of hot gas molecules. That breaks the second law. So to make sure the total entropy of the universe goes up, the engine must dump some of its energy as low-quality, useless, disordered waste heat. It's like a cosmic tax, and it is absolutely unavoidable.
Okay, so
These laws are unbreakable. They set the rules of the game. So now let's take a look at how engineers have gotten so brilliant at working within these rules to build the machines that power pretty much everything we do. So there are really two main ways to play this energy game. A heat engine, like the one in your car, cleverly takes advantage of the natural flow of heat from a hot place to a cold place, and it basically skims some of that energy off the top as work. But a heat pump, think your refrigerator or your AC unit, it does the exact opposite. It uses work to force heat to go against the flow, from a cold place to a hot place.
Let's just walk through a really basic heat engine cycle. So, step 1, you add energy. Heat from burning fuel gets pumped into a gas inside a cylinder. This makes those gas molecules go wild, moving faster and slamming into the cylinder walls, which makes the pressure skyrocket.
And now for the magic moment. That incredible pressure forces the gas to expand, and in doing so, it pushes a piston outward. This is it. This is the useful work we were after. We've just turned the random thermal energy of a hot gas into useful, organized mechanical motion.
But hold on, the job's not done. To get that piston back to where it started so we can do it all over again, we have to cool that gas down and lower the pressure. And how do we do that? Well, we have to release waste heat into the colder air outside. There it is again, that mandatory entropy tax we talked about, paid in full every single cycle.
So, the way we measure how well an engine is doing its job is called its thermal efficiency. It's just a simple ratio. You take the amount of useful work you got out and divide it by the total amount of heat energy you put in. You can think of it like the engine's final grade on a report card.
And this chart right here shows you what that report card looks like for a real-world coal-fired power station. For every 100 units of energy you get from burning the coal, a really good, highly optimized plant might turn about 41 of those units into useful electricity. And the other 59 units? Yep, that's the unavoidable waste heat just vented straight out into the environment.
So, at the end of the day, these laws of thermodynamics give us this really profound way of looking at the universe. Energy is always conserved, sure, but its quality is not. It's constantly degrading from useful, orderly forms down into useless, disordered heat. The arrow of time is always pointing towards more and more entropy. It's like they say, you just can't unspill the milk.
Which leaves us with one last massive question to think about. If the total disorder of the universe must always increase, and all the useful energy is slowly, inevitably turning into useless, evenly spread out heat, what does that imply about the ultimate fate of everything, of the entire cosmos?